Like the title suggests, this video is going to be pretty much going over, what are the basics of covalent bonding? What are the fundamentals? Well, the very first basic that comes with covalent bonding is, what type of atoms actually do it? And so, remember, don't forget, when you're thinking about the periodic table, there are very, very straightforward types to consider. You have your metals, you have your nonmetals, and then technically speaking, you have your metalloids, except I'm not really going to cover that. We can just kind of deal with metals and nonmetals, and that's it. And so, to have another reminder for that, what that means then is that if we're not really going to be thinking about the metalloids, I'll color them in. So it's these guys, right? These 7. This is the metalloid ladder. And then the thing that I want to make clear is that you can use that metalloid ladder again to kind of tell you where your metals are at and where your nonmetals are going to be at. And all you need to do is memorize those 7 elements, and you're pretty much good to go. Once you have that, you realize then that what you have over on this side over here, these are your nonmetals. These guys over here on the left, those are your nonmetals. Do not forget to count hydrogen, because hydrogen technically belongs to them. And then essentially everything that you have on the left is metal. Now, with ionic is when you combine a metal with a nonmetal, and that has its own reasons. That should be covered in an ionic bonding video. And if we're talking about covalent bonding, then what we're talking about specifically is this is the type of bonding that happens when you have nonmetals interacting with nonmetals. So, again, for covalent, when you're thinking about a covalent bond, because that's really what we're talking about. For a covalent bond, you're talking about a nonmetal combining with a nonmetal. Now, remember, the whole reason of a covalent bond is that in covalent bonds, you share electrons. That's the whole point. You want to share electrons. And let me actually write like a normal human being so you can actually, read my handwriting. But that's kind of the idea, right? You share electrons. Why do you share electrons, though? While we're here, we might as well talk about that. Look, nonmetals, if you focus on the fact that we're looking at an electronegativity table right now, nonmetals all have the highest electronegativities on the table. In fact, most of the electronegativities are above 2. You have hydrogen coming in at around 2.2, 2.1, depending on the table that you're looking at. You have fluorine coming in at around 4, being the highest. But they all generally tend to be a lot higher than metals. And so nonmetals, because they really want to take in electrons, because if you notice, we're talking about group 4 all the way going over to essentially, 8, although we don't really count 8 too much for covalent bonding, but these guys are all guys that are very electronegative, and so they all want electrons. And so when you pit a nonmetal versus a nonmetal, the difference in between them is going to be so small that they have no choice but to share electrons. And so when they share electrons, well, how do they share them? And how can we actually predict that? And I'm going to tell you right now that for covalent bonding, the prediction is actually very simple, so long as you keep 2 rules in mind. The first rule is you need to be able to draw Lewis dots. And so the very simple one to start off with is we can look at chlorine versus chlorine. So chlorine is going to have 7 valence electrons because, again, chlorine right here is in group 7, right? 7 right here. That's where we have chlorine. So there's going to be 7 valence electrons. And then the other chlorine is also going to have 7 valence electrons. And the very key thing that you need to understand, and this is why Lewis dots need to be drawn correctly, is because if you see this, you start to notice something very, very important. And what's important is that if you check to see what happens to that last valence electron, is that last one is unpaired. When you have an unpaired free electron that is not stuck in a lone pair, they can bond. And that's the biggest takeaway that you can take from this, is that those guys have essentially free electrons. They're going to look at each other and they're going to be like, hey, I have a free electron, you have a free electron. Why don't we figure something out? And so if you take this to step by step and you kind of go along, well, those electrons are going to be shared in the center. Octet rule is still driving everything. They both desperately want to have their octet. Sharing is their only option available because of the electronegativity, and so they complete their octet. This, again, you can rewrite it as a line to represent a pair of electrons, and when you have that, you're pretty much good to go. You just kind of see that, and this pair of electrons is equivalent to this line, and you're pretty much good to go. Okay, now the thing is, you see one shared pair of electrons, and then you see this one line. This is called a single bond. And that's going to be very, very important, because that is going to lend itself towards, how is it that covalent bonds form and how many bonds can each element make, which is kind of its own thing. That number, how many bonds they can make, is going to be related to how many free electrons they have. So if you draw Lewis dot structures inappropriately, as in you don't realize how many unpaired and how many paired electrons they have, you kind of get rid of your only tool that helps you understand how many bonds things are going to make. Now, here's the thing. If we look at something like the halogens, now let me actually get rid of this. It's a lot of it, but I need to get rid of all of it. Okay. If we look at the halogens, we start to realize that they all have 7 valence electrons. You look at what is it? Fluorine, chlorine, bromine, iodine. Those are the main ones I'm going to focus on. Those guys are all, the halogens. They're in group 17. You see that there. Those guys are all going to have 7 valence electrons, and so they're going to have 3 lone pairs. Each one of them is going to have 3 lone pairs. And then let me actually draw the ones for chlorine. But each one is going to have 3 lone pairs. But then there's something very important to make note of. Each one of them is going to have 1 unpaired electron that is going to be available for bonding. And so just like this, you can pick up a very simple rule. And the very simple rule then is that halogens, based off, their normal tendencies, what they like to do normally, because, you have to understand that this pattern does break occasionally, is that they all generally tend to like to form, 1 bond when you actually bond them covalently. And you can just see that based off of the fact that they have a free electron. Okay, well, let's consider kind of the alternatives. Well, the other alternatives is to consider group 6, which is the next one. Although for that one, we're just going to think about, just oxygen. So if we're thinking about oxygen, let me get rid of all this superfluous crap that we don't really need anymore, because, we're just focusing on the nonmetal, so we're just looking on the right side. If we think about oxygen, so there's oxygen. It has 6 valence electrons. If you draw it correctly, you should realize that there are 2 lone pairs, and then there are also going to be 2 unpaired electrons, assuming that you do draw it correctly. The biggest thing that you want to make sure that you focus on is the fact that, well, look, you have 2 unpaired electrons. Electrons like to be paired up. Now, this is going to lend itself to this idea that those 2 electrons on each oxygen are going to pair up to make 2 pairs. And what that looks like then is you have oxygen coming together with oxygen, where each one of those pair of electrons come together. There's 1 pair. There's another pair. And then the lone pairs that you had are still pretty much going to be on the outside. The only thing that happened was that those unpaired electrons essentially paired up in the center. And remember what I said, each pair of electrons, when they're kind of in between 2 atoms, they represent a bond. And so one way that you can rewrite this is like this. You show the 2 lines to essentially represent the 2 bonds. And so this right here is your first understanding that there is such a thing as a double bond as a possibility. But you have to realize that only certain elements can undergo a potential double bond. It doesn't even necessarily mean like they're going to do it. And that all depends on how many free electrons you have available and whether or not it's going to be possible. And so, that's one option. But really what that's telling you then is that if you're thinking about, the group 6 elements and so on and so forth, for group 6, you're talking about, oxygen, you're talking about sulfur, you're talking about selenium. These guys are going to have those 6 valence electrons. They're all going to be very similar to each other. And so what that tells you then is that if you focus on the fact that they have those 2 free unpaired electrons, they have the possibility to make 2 bonds. Now again, this is just the basics. I will tell you that there are some exceptions. We're not going to go into them right now. But again, the one thing that you want to focus on is that because these guys have these unpaired electrons, there's 2 of them, there is a possibility to make 2 bonds. Now that could mean that you make, 2 single like that, where they might go off in different directions. However, there's another possibility, which is if you do have enough of the possibility, the oxygen can actually double bond and it'll be happy, where two bonds are going to the same atom. Two possibilities, and that's kind of the basics for that. Okay, so then let's look at group 5, where group 5 has 5 valence electrons, and then we consider about what's going to happen there. And with group 5, really you're only going to be working mainly with nitrogen and phosphorus if you're really just thinking about nonmetals, at least for the basics for right now. So when you have nitrogen, just to kind of consider nitrogen, you have 2 electrons that are kind of stuck in a lone pair, and then you have 3 free electrons that are available for pairing and bonding. And if you were to take 2 different nitrogens and you were to kind of put them side by side, you begin to realize that there's a pattern forming, which is when you have those 3 free electrons, you're probably going to think that those 3 different free paired unpaired electrons on each atom are going to pair up, and so you're going to get 3 pairs kind of in the middle. And so it might look a little something like this, where you have N and then 2 of those pair up, another 2 pair up, and then another 2 pair up, and so you have 3 pairs in between the nitrogens. You still have the regular lone pairs that you started with on the outside. And so when you have that, another way to rewrite that would be, just keep it very simple. N, 1, 2, 3 bonds with the lone pairs kind of sitting out. Everyone has their octet, everyone has their 8, everyone's happy. And when you have that, then, this is your first introduction to the possibility of a triple bond. There's your triple bond, where if you have 3, unpaired electrons, you have that possibility. Okay, well, you have a triple bond there. So what are the potential possibilities for this? Because for the oxygen, there were 2 possibilities where, you had, the opportunity of having 2 bonds going off to different directions, or you had 2 bonds focusing on one atom. Well, this one is going to have, a slightly different consideration. It's just really messing around with the possibilities, where you can have a nitrogen where you can have the straight up nitrogen where if you think about the different bonds, you will have this free electron, and this free electron pairing up to make 1, 2, 3 single bonds. That's one option. You also have the possibility of making something look like this, where if you have a nitrogen, again, you still have the unbonding lone pair that's there, and then you might have 2 bonds going towards one atom, but then you have 1 single bond going towards another. That's another option, because again, that's still using up the 3 unpaired electrons. They just, shift around and they go to a different spot. And then finally, the last option that you have available is you have, 3 bonds going in the same direction towards one atom. And granted, that's only going to happen if you have enough of a space available to be able to do that, which isn't a guarantee, but that's the idea. So these are all the different bonding possibilities. If you have 3 unpaired electrons and the possibility to make 3 different bonds, you can start to see how little by little this is getting more and more complicated. Okay, so now we need to get to the last group, which is pretty much, what happens when you get to carbon. What happens when you get to carbon? And I'm starting to realize that there's going to be something I'm going to say that might accidentally anger you, because I'm going to have to hide it behind a veil and not tell you why it works the way that it does. There is a reason why, and it has to do with orbitals and how they mix together. But pretty much once you get to carbon, if you look at the valence structure for carbon, you have 4 free electrons. That should kind of give you a hint that those 4 free electrons are going to be available for bonding, for sharing. And you would think, right, that when you're looking at that you're going to be like, well, the possibility is very simple. What if we make a quadruple bond? Never do that. Ever. Never, ever, ever do that, because that's actually not physically possible. It is not physically possible. There is a reason why. It has to do with something called orbital hybridization. If you want to pause this video and go look it up to see what I mean, go ahead and do that. But this is not going to be the topic of the video. We're just going to keep it basic. That is not possible. However, if you're thinking about carbon, okay, well, look. Okay, quadruple bond, not possible. Well, what about a triple bond? That actually is possible. And in fact, when you do a triple bond, what that means then is you're going to be having a triple bond going this way, and then a single bond probably going the other way. Well, what about a double bond? Also possible. You can have a double bond and a double bond going that way. There's your 4, right? Okay, well, what about, 4 singles? Yeah, 4 singles is definitely a possibility, and in fact, that's one that's going to show up a lot. But then you can start to mix and match because you have another option available, which is, okay, well, what about having, a double and then 2 singles? And you start to see then that when you look at carbon, one of the reasons why carbon is so important and one of the reasons why life is actually made up of carbon is because now you're starting to see that even just kind of working with one element, you have a gigantic number of possibilities, and everything is going to get way more complicated from here. But pretty much there was a trend, and it was a trend that I hope that you guys kind of spotted, and it's a pattern, and really it's something that is a very basic rule, and I like to use it as something that's like basic, and I might later go on into a more deeper launching point because I'm gonna tell you right now the general rule of thumb doesn't actually work all the time, but here's what you should have seen. That way I kind of stopped talking about it. What you should have seen really was that depending on how many free electrons you had, that actually kind of told you what kind of bonding you were going to be making and how much bonds you were actually going to be making. So if we move this down, look, let's say we're talking about something like hydrogen, which only has that 1 electron. That's available for bonding. You have, chlorine, fluorine, the rest of the halogens that have that 1 free electron available for bonding. And let me actually color it with a different color that we can see it. So that electron is free for bonding. And then you have, all the other ones that are the halogens, which is like iodine, bromine. These guys you can consider to be in the category where, because they only really have that 1 electron, the general tendency is that they're all going to kind of just make one bond, right? So if we kind of section this off, we'd be looking at this guys and we'd be like, all right, well, they can make one bond. Now, is that always going to be the truth? No. I mean, there's always going to be exceptions, but in general, the rule of thumb is something very simple you can follow. Okay, well, what about the ones that can make 2 bonds? Well, the only ones that can really make 2 bonds are pretty much group 6, where if you look at oxygen, because again it has those 2 free electrons available for bonding, and then you have sulfur, just to give an example. I'm not going to draw all of them. Selenium would be the last one, but it's again just a very simple idea that if you kind of look at the free electrons that are available for bonding, these guys will generally have the capacity to make 2 bonds. And then the last thing that you kind of want to see is, well, okay, what about 3 bonds? Well, N. Well, why? Because nitrogen and phosphorus, if we look at both of them, they can generally have those 3 free electrons that are ready to pair up should the need arise. And, they're there, so then what are the possibilities? Well, these guys can make 3 bonds. And then, the last one, which is the one that's probably the most versatile, is when you have carbon, you technically have those 4 valence electrons that are available for bonding. And so in that case, this guy can make 4 bonds. And so what you see then, and this is probably the most important part, is that you see H, O, and C. And H, O, and C are the ones that kind of always show up in organic molecules, so stuff like you and me, alcohols, gasoline, things like that, just organics that are carbon-based and so on and so forth. That right there is kind of why there is this thing called the HONC rule, which is HONC, 1, 2, 3, 4. And the HONC rule is actually what people use to start to build molecules. That is going to have to be an entire video on its own, because the hardest part about doing that is keeping track of all of these rules. But I really do hope that if you manage to see the pattern in the valence electrons and how that tells you how they're going to bond, and you realize that so long as you're working with nothing but nonmetals, you kind of are just going to have covalent bonding, that's going to be enough to give you a basis on which to kind of take everything further. And so I hope that made sense.